Welcome to the wonderful world of physics. This is the last section of chapter 25, section 5, capacitors in circuits. So far, we've considered only circuits with a steady current. A flashlight is a good example. If you turn it on, a current starts almost instantaneously, and then it continues flowing steadily until you turn the flashlight off. But now, when we add a capacitor to it, circuit quantities are going to change more slowly. So that's what we're going to look at. We're going to look at in this section RC circuits. Now RC circuit stands for resistor and capacitor. And what it means is we're going to have a resistor and a capacitor in series like you see in the picture at the top of the page. RC circuits are used in a variety of electronics applications as timers. So because of the changing nature of quantities in the circuit, it can be used as a timer. Now you look at this picture, here we've got a battery, we have a switch, a resistor, and a capacitor. As soon as you close the switch, current will flow immediately. Electrons will flow, let's follow along with my pointer, they'll flow from the negative terminal. Now imagine the switch is closed. Or we can look down at this picture down below with the closed switch, through the resistor, and they will accumulate on the capacitor's upper plate, on that negative plate. Electrons will flow into the positive terminal, leaving positive charge on the capacitor's lower plate because they left the lower plate, so leaving it positively charged. And as the charge builds on the capacitor, the voltage across it increases. And remember that voltage on a capacitor, the voltage difference is charge, the Q that's on each plate, negative Q on the top plate and positive Q on the bottom plate, divided by capacitance. Now the current is going to be reduced until the voltage across the capacitor equals the EMF of the battery. And at that point, if the voltage drop across the capacitor is the same as the battery, what we can infer from that is that there's no voltage drop across the resistor, which means there's no further current flow. Because by Ohm's law, voltage drop across the resistor is current times resistance, but there is no voltage drop, and so that means that the current is zero. The voltage across the capacitor increases as time goes on. Now I'm going to derive this. Let's look at this picture down here. We're assuming the switch is closed. And even though earlier on this page I talked when we were looking up at this picture, I talked about how the electrons flow in a clockwise direction. Remember that positive current goes in the opposite direction. So now let's think in terms of the way positive current goes. We're going to talk about it going counterclockwise. Now we're going to use the loop law, and depending on what videos you've seen, what lessons you've gotten, you may not have encountered the loop law yet, but here is the loop law. It's actually covered in section 25.3. And so it's possible you haven't gotten that lesson yet. But the loop law is that we follow the voltage and we subtract the voltage drop. So going around following the current, we have stepping up the electromotive force, and then we're going to subtract the voltage drop across the capacitor, and that's Q divided by C. And then we're going to subtract the voltage drop across the resistor by Ohm's law, that's current times R. And when we make it all the way around to the battery on the other side, the total of the voltage should be zero. That's what the loop law is. The battery steps it up, and then that same voltage gets dropped down, and it comes out to be zero. Now I'm going to do a bit of derivation to get to the mathematical equations that we'll see on the next page. Remember that current simply is the rate of change of charge, the rate of passage of charge. So it's dq over dt. I'm going to take the time derivative of this equation. So here it is, time derivative, And then when we take the time derivative of each of these parts, the time derivative of EMF is 0 because that doesn't change, minus capacitance doesn't change, so we move it to the side of the time derivative, and it's 1 over C times dq dt minus di dt times R equals 0. So again, this last line on the page is just the time derivative of this loop law equation. There it is up above. Now I'm going to get rid of the zeros, move things around in this equation, and we're left with R di dt, that's this last term here, equals negative I over C. Moving things around a bit more, that gives us di dt is negative I over RC. So what this means, the left-hand side refers to the rate of change of current. So this is something new for us in this class. Before, we've just turned on the switch and there was steady current. Now we've got a time-changing current. The rate of change of current is proportional to the current itself. And that negative sign there means it's exponential decay. So here's what it looks like when we have an RC circuit, a resistor and capacitor in series with each other. We close the switch, we turn on the circuit, and the current immediately starts at some high amount, relatively high amount, and then it goes through exponential decay. Now let's find a time-dependent equation, what the time-dependent function of current is. Now I'm going to take this equation that's in the box, and I'm going to turn it around in such a way so I can integrate. So I've got di over I equals negative 1 over RC times dt. I'm going to integrate both sides of this equation. So on the left side, we've got the integral, and I'll just right now take the limits of integration from I naught to I, and the limits of integration for dt are from 0 to t. So as soon as we close the switch, we turn the circuit on, the stopwatch starts at time equals 0. And what this is going to allow us to do is figure out what is the current at any given time. Now, these limits of integration that I chose for I naught is the current at time equals 0. And that's actually the instantaneous, as soon as you turn on the switch, there is the full current that you would expect if there hadn't been a capacitor in the way, and it's just voltage divided by resistance. That's what Ohm's law tells us. So at the moment the switch is closed at t equals 0, it starts at I naught, and then it's going to go to some other value of I for the given time. Well, taking these integrals, the integral on the left-hand side, and I hope you're do these at home. They're pretty simple integrals here, but make sure you follow the integration I'm doing. But that becomes the natural log of I over I naught. On the right-hand side, after we've moved the negative 1 over RC out to the side of the integral, it's simply negative t RC. And now once we have this part, we're going to solve for the current. So you can see step by step, I've taken that logarithmic equation, turned it into an exponential equation. It's e to the negative t over RC equals I over I naught. Move things around a bit, and in the end, the derivation of the last page is this, that the current as a function of time is the EMF over resistance times E, now that's lowercase e, which is the base of a natural log, to the negative t over RC. So even if you never do this derivation again, this equation at the bottom in the box is what you'll need. Notice what's going on here. It starts with EMF over R, meaning when time is 0, that's what it is. That's exactly what we would expect, again, if we just had a battery with a resistor. But introducing a capacitor in there with the resistor gives it this exponential decay. And as time goes on, as t gets bigger, this is going to approach 0, as you see in the graph at the middle of the page. There it is again at the top of the page. Well, we've just solved for what is the current, the time-dependent current. Let's talk about the time-dependent electric potential or voltage across the capacitor. We'll start again with the loop law. And again, the loop law says if we trace the current around, we start with adding the EMF voltage and then subtracting away the voltage across the capacitor and the voltage across the resistor. And by the time we get all the way around this loop or this circuit, it should be back to zero. So EMF minus voltage across the capacitor minus voltage across the resistor is equal to zero. Solving for voltage across the capacitor, we get EMF minus V sub R, voltage across the resistor. And then we can say, well, voltage across the resistor is current across it times resistance. But remember, that current is changing. It's dependent on time. And so in the next line, I'm replacing the current across the resistor with what's here in this green box at the top. And when you multiply it by that R, we get EMF times little e to the negative t over RC. So the voltage across the capacitor is, in simplified form, this equation here in the green box at the middle of the page. I factored out the EMF. So it's EMF times 1 minus e to the negative t over RC. Now let's think about what that means. Again, if there were no capacitor involved, if it were just a resistor, the voltage across, well, I'm sorry, I'm going to back out of that statement because we're looking at the voltage across the capacitor, so never mind. Okay, voltage across the capacitor is what we expect it to be. I should have said if there were no resistor right here. So the voltage across the capacitor is the battery. But then there's this time dependence, 1 minus e to the negative t over RC. It's like exponential decay, but it's got a minus sign in front of it, so it's inverted. It's 1 minus exponential decay. And so we're not going to call it exponential growth. That's something different. Exponential growth is where it starts at 0 and goes up towards infinity, but rather this is inverted exponential decay. So it slowly grows. If we plug in different values for the exponents, so negative t over, and let's just say that R times C is time, that is the time. So let's replace little t with R times C. Now R times C as time, that sounds kind of weird. Resistance times capacitance, that gives time. And yes, actually it does. I'll explain that in a bit. But let's just say that the time is whatever R times C is. You take however many ohms it is times however many farads of capacitance, and that's how many seconds. Well, at that time, you get 1 minus e to the negative 1, and it's at 0.63. So follow the graph here. At RC, at a time RC, it's at 0.63 times the battery's voltage. If the time is twice RC, then it's e to the negative 2, and you're at 0.86. At 3 times, it's 0.95. And so what that means when we say 1 minus e to the negative 3, that just means that the time, however much time has gone by, is 3 times whatever R times C is. And you can see it slowly then approaches the voltage. So by the time it gets to 5 times, the time is 5 times RC. The voltage across the capacitor is 99% of the battery. And so we can ask the question, when will the capacitance be at full voltage? Meaning whatever the voltage across the battery is, that's the voltage across the capacitor. And really, precisely speaking, never, because this asymptotically goes to time, to infinite time. It approaches that. But we can say that for practical purposes, at 5 times RC, it's close enough. That capacitor is about as charged as it's going to be. It's at 99%. And I just mentioned charge. Let's talk about that. Remember that charge on the capacitor plates is capacitance times voltage. So we can also say that the charge at 5 times RC is 99% of its maximum charge. You can wait longer. You can wait to 6 times RC or 7 times RC, but you're not going to get that much charge given that extra time. It's close enough charged when it's at 5 times RC. Now, I've been relating this idea of RC, talking about time, and yes, the dimensions are time. So I want to introduce to you this idea of the time constant, and that is the Greek letter tau there. It's not a T, it's not a capital T or a lowercase t, it's the Greek letter tau. It's written like a pi, but it only has one leg to stand on. And the time constant for an RC circuit is simply the resistance of the resistor times the capacitance of the capacitor. So as I said on the last page, when will it be fully charged? Well, never, because it would take to get to 1 minus e to the, it would have to be negative infinity. But for practical purposes, when it's at 5 RC, we say that it's fully charged. I showed on the previous page at 5 RC, it's 99% charged. At 7.6 RC, it's 99.95% charged. Now, the application, as I said before, it can be used anytime you have electronic components that have a timer function. So a digital clock, the clock in your phone, anything that has a timer, it needs RC circuits to keep that time. And if you find yourself in a more advanced electronics class, a simple project that you'll do is building a timer, building maybe a countdown timer that counts down from 60 seconds. And you have to introduce elements, RC circuit, that will make it keep proper time. Other applications of timers are windshield wipers. Windshield wipers are on a, you can have them slow or fast. Well, that has to do with a resistor and a capacitor, and the various resistance and capacitance change the timing. As I said, digital clocks and timers, pacemakers also. The current is, remember, it is the EMF divided by the resistance times that e to the negative t over RC. And so again, there's that exponential decay of the current. The dimensions, let's do some dimensional analysis of an RC circuit, just to show you that R times C is actually time. We'll start with R times C, and let's just think about the units on those, ohms times farads. Well, from Ohm's law, we get that, that an ohm is a volt over an ampere. We've also seen that a farad is coulombs divided by volts. Don't confuse your capital C, because we see that as capacitance and also coulombs, but I'm looking at units here. So it's coulombs over volts. And so that becomes, the volts can cancel out. We have coulombs over amperes. Think of an ampere as a coulomb per second, and there we have seconds. So yes, resistance times capacitance actually gives time. Now that our capacitor is charged up, let's discharge the capacitor. And the way we can do that is, you see the picture there. We have the capacitor and the resistor linked. Notice the battery is out of the picture, and we can work the circuit so as to remove the battery, have open the switch connected to the battery. And now we've just got the capacitor and the resistor, and we've got that switch. And so as it is right now, our capacitor is fully charged. We just spent the last few minutes charging it up, or talking about it, getting charged anyway. So initially, it's at its full voltage, it's at its full charge, and it doesn't necessarily have to be at the maximum that, we wait 5 time constants and it gets fully charged. We could have just charged it up halfway and then opened the circuit, only got it charged halfway. So I'm going to call the initial voltage and charge V0 and Q0, whatever those are. The voltage across the capacitor is time dependent. I'm not going to derive this. The derivation actually is very similar to what I did in the previous few pages on this video, but I'll just give you the equation. The voltage across the capacitor is V0, which means whatever the initial voltage was. Then we discharge it. We close the switch. It's V0 times e to the negative t over RC. So it is exponential decay. And because charge is simply capacitance times voltage, they are related to each other. The charge on the capacitor is whatever the initial charge was, times e to the negative t over RC. So here you have, I've just drawn a voltage graph. After RC, it's down to 37% of whatever its initial voltage was. After 2 RC, it's down to 14%. By the time you get to 5 RC, it's discharged close enough to 0, probably about 1%. Let's look at an example. Let's say that we have an RC circuit. It's already charged, and the capacitor is charged to 35 microfarads. It's connected to a resistor of 120 ohms. The question is, how much time until the voltage across the resistor falls to 10% of the original value? So we're going to discharge this capacitor. We want to know when it gets to only 10% of the original value. We're going to use the equation for discharging a capacitor, and when you're doing these problems in the homework, make sure that you keep straight there are separate equations for charging the capacitor and discharging the capacitor. So here we are discharging. So we have voltage across the capacitor is V naught times e to the negative t over RC. And algebraically, we need to do what we have to do to solve for time. So let's get rid of that V naught by dividing both sides by V naught. In the second line, we have an exponential equation, and we want to get inside that exponent, which means we need to turn it into a logarithmic equation. Easiest way to do that is take the natural log of both sides. That gives us on the left natural log of VC over V naught, and on the right, negative t over RC. And we solve that for t. We get t equals negative RC times natural log of VC over V naught. We can plug in those values. Now, the bit that I've done in purple, and actually I wrote something incorrectly, so let me, I need to put in a little decimal here. The time constant, there we go. The time constant is 4.2 milliseconds, so just doing R times C. The time constant for a RC circuit is a useful measure. It gives you a ballpark figure of what kind of timing is going to be occurring with this RC circuit. Meaning, are we talking about microseconds, milliseconds? Are we talking about seconds? What roughly is the amount of time we can expect? So the time constant, RC, 4.2 milliseconds. So pretty much any question we're going to ask about this RC circuit, about timing, is going to be in the range of milliseconds. All right, so it's 4.2 milliseconds times natural log of 0.1, because VC over V naught, it's reduced to 10%, and we get 9.7 milliseconds, which, by the way, is 2.30 times the time constant. So our ballpark figure of what timing we could expect was 4.2 milliseconds, and it's going to be more than that, so 9.7 milliseconds. And you should also know this is a useful equation to write down for any specified voltage, just to use this equation. So I've already gone through the math here. Now notice the difference. Look what we've done in the green. Look where my pointer is. It says T equals negative RC times the natural log of VC over V naught. And that right there is a good equation that you can use. If you know the voltages and you want to know the time, just write down this equation. It's a handy formula. But you notice what I've done in the box down below. It's a little different. I've done two little changes just to make it a bit more concise. The negative sign is gone, and I flipped these two, V naught over VC. So that's following some laws of logarithms. The negative is, and you just flip that fraction. And you can test it out to make sure that that does in fact work. Let's do example 25 in the book. It says a camera flash gets its energy from a 150 microfarad capacitor and requires 170 volts to fire. If the capacitor is charged by a 200 volt source through an 18 kilo ohm resistor, how long must the photographer wait between flashes? Assume the capacitor is fully discharged with each flash. All right, I've written out the given information. Capacitance is 150 microfarads. We need voltage across the capacitor to be 170 volts for this thing to work. The EMF of the battery that's supplying the voltage, 200 volts, and we've got an 18 kilo ohm resistor. And we want to know about charging it. How much are we going to wait to charge it? And so we have VC equals EMF times 1 minus e to the negative t over RC. And again, make sure you keep straight what are your equations for charging an RC circuit or charging a capacitor in an RC circuit, and what are the equations for discharging it. But in this problem, we are charging, so we'll use this equation. We're going to solve for t, and we'll go through, similar to what I did on the previous page, we need to solve for t little by little. So let's first get VC over E is 1 minus e to the negative t over RC. Then e to the negative t over RC is 1 minus VC over E. And excuse me, I'm saying E for both of those, so it might not make sense if you're not reading along. There's little e, and then there's EMF E. And we'll take the natural log of both sides. So the natural log of 1 minus VC over EMF is negative t over RC. Finally, we'll multiply both sides by negative RC. So in the end, we get time for the charging of a capacitor in an RC circuit is negative RC times the natural log of 1 minus VC over E. We plug in those values. I've started by just doing, again, in the purple ink, just the time constant, RC, 2.7 seconds. That gives you, again, a ballpark estimate of what kind of timing we can expect. So it's in the range of seconds. But then, let's see for this particular example, times the natural log of 1 minus 170 volts over 200 volts, and we get 5.1 seconds, which, by the way, based on that natural log, that is 1.9 times the time constant. And that is the end of Chapter 25, Section 5 on RC circuits. Have a great day.